All right, so this is a past HSC question, and what you'll see is the ones that we've been seeing are just using linear drag, not quadratic drag, because then we can use something we've done before, separable differential equations. So we can actually do calculus with them. So if you look at this one, it's just particle, it's got a mass m, it's thrown off a tall building, initial velocity u, angle alpha. It experiences both gravity and a resistance, which is proportional to its velocity, so it's just linear. So we end up getting these equations of motion that they've given us. And the first question is to derive the result x dot. So of course we'd use x double dot and we'd integrate to get x dot. But how do we do that? Well, remember x double dot is, so we're using this equation here, is just d beta t of x dot. Same thing as x double dot. All right, so if you think of differentiating x dot with respect to t, if I put all my x dots over on this side, so here's my x dot one, so I'm just moving this one here and integrating it, with respect to x dot. There we go. And then everything else on the other side, so separable equations here. So I'm differentiating with respect to t here. All right, in that case, just think of our limits. So x dot wise would be our horizontal velocity. So horizontally, if we've got a certain velocity here, we are going from, if it's u to start with, this would be u sum of sine alpha, and this would be u cos alpha. So our initial velocity is u cos alpha, and we're going to some value of the velocity, so up to x dot. All right, so over this side it's nice and easy. We're just going from 0 time to some time, so minus kt over this side. On the other side, we are going to, of course, get log of x dot, and when we put that all in, we're going to get log of, I'm going to do it, so we've got x dot, no, I'll do it properly for you. All right, so we're going to have log of x dot, and we're going between u cos alpha and x dot. So I'm going to get log of x dot on, so minus log of u cos alpha equaling minus kt. Now if I exponentialize both sides, I get x dot on u cos alpha being equal to e to the minus kt, so that has to be positive. I don't need the absolute values. We know what e to the minus kt looks like, and if I just multiply the u and the cos alpha onto this side, I get the result that I was after. Yep, so I get that result. Oops, that's good. All right, so part 2, we have to verify that y dot. So this is what you're used to with like exponential equations when we did rate of change things. So y dot. So what we do is we differentiate and get y double dot, and we express it in terms of y dot. Do you vaguely remember that? So you can see y dot is expressed in terms of y double dot is expressed in terms of y dot. So that's what we're going to do. We're going to differentiate y dot. We're going to get y double dot and express it in terms of y dot. And hopefully we get back to this equation. That's how we verify that this satisfies the solution. And then of course we want to look at the initial condition as well, but we'll do that next. All right, so if I start with my y double dot, so what is y double dot? It is d beta t. Actually, I'll start with my y dot because that's what I'm given. Sorry, y dot, and I've got 1 on k, and then I think I need a smaller pen here. 1 on k, ku sine alpha plus g e to the minus kt minus g. Alright, so if I'm differentiating with respect to t, mind you, to get double dot, I'm differentiating with respect to t. The only t you can see in there is here. It's an e to the minus kt. So if you think about that, we've got 1 on k, and that negative k from here is going to come down to the front. So negative k, but all the other stuff will still be in there. Ku sine alpha plus g, lots of e to the minus kt. Of course, minus g doesn't have a t in it, so nothing happens there. So I just get all this, which is equal to minus, now I need to express it, remember, in terms of y dot. So this is going to become a minus 1, but I want a 1 on k, so I can go minus k and times it by 1 on k, and that's still minus 1, because I wanted that 1 on k. I've still got the ku sine alpha plus g in there, e to the minus kt. So that still works nicely. But remember, what I do want is I want this minus g. So what I could do is just minus a g, so it's nice in there, and then I can also add a g. Now, I could do that if I have a look at, if minusing that g, remember this is equal to negative 1. So that minus g, if I look, yes, sorry, that's in that bracket there. So I could just go, that minus g is like a plus g if I times it by this stuff out the front. So then I could just balance it outside. And why I want to do that is because the stuff on this inside part here is equal to y dot. So now I have minus k, oops, that's a bad minus k. I have y dot and then minus g. I mean, you do know what you're heading for, so you can even, use that to help you. So that's all well and good. Does it satisfy the initial? So that means, yeah, it's a solution. Does it satisfy the initial conditions? Well, let's check. Let our t equal 0 for our y dot. What happens to our y dot when t equals 0? Let me just wrap this out a little bit. So when t equals 0, we still have the 1 on k, but in here we have ku sine alpha plus g times 1, right, times 1, and then that part is so hard to see when you're looking on the side, and then you have a minus g. Is that right? Okay, so I'm looking over here and putting t equals 0 in because I can't read my own writing. And so what we'll get is just u sine alpha, which is what we want, isn't it? That should be the initial condition. There we go. So our y dot should equal u sine alpha. So yes, this part 2 we've verified. So part 3 then, find the value of t when the particle reaches its maximum height. Now we know when it reaches its maximum height, we know that y dot should equal what? Y dot should equal, so at the maximum height, y dot should equal 0 because it turns around. So its vertical velocity is 0. So let's use that equation that we just had there and make it, this equation, make it equal 0. So if we do that, we've got 0 equals, and it says 1 on k, but that's if I times by 0, that's going to be a 0. So I'll just look at the inside, and I've got ku sine alpha plus g e to the minus kt, and I've got minus g, so I'll add it to that side, so that equals g. So if I want t, don't I? So I'll put this on this side, so e to the kt, and then this will be ku sine alpha plus g all over g. And then if I log both sides, I have the log of all that stuff. And then if I divide by 1 on k, I get 1 on k log. So I've got ku sine alpha plus g on g. And that's what it would be. So that would be the value of time, t, when the particle reaches its maximum height. It's not very exciting, it's a bit ugly, but that's what it is. All right, and then if I look at the next bit, what is the limiting value of the horizontal displacement of the particle? So limiting value, we're talking about as time goes to infinity. And what's happening to the horizontal displacement? We're interested in x here. So what is x equal to? Well, let's have a look at x. We could say if we integrate x dot, we get to x, right? So let's integrate x dot to get to x with respect to time. And for time, we're going from 0 to infinity if we want the limiting value. All right, so x dot we know is u cos alpha times e to the minus kt, because we have that right here. So always looking for something to use. So we are integrating, or u cos alpha is just a constant. So which bit has the t in it? We have e to the minus kt that we can integrate with respect to t. So I need a divide by a, so I need an over negative k, so I need to times by a negative k. I need to divide by a negative k, goodness gracious. All right, so if I had a negative k here, then I could divide by and get back to e to the minus k, so I'd need a negative k here as well, if that makes sense. So I've got negative u cos alpha on k, and here, now when I integrate, I can go straight to this. All right, now let's have a think about what happens as t goes to infinity. Remember, e to the negative kt is the same as 1 on e to the kt. So as t gets really, really big, this goes towards 0. So really, this is all going towards here. So what are we going towards? Well, this would go 0 minus, when I put 0 in there, I get 1. So you can see it's going towards u cos alpha on k. So the limiting value of the horizontal displacement, so it goes towards u cos alpha on k as a horizontal distance.